A lot of the motivation for what I'm going to talk about has already been laid out by the previous speaker. So I'll start by showing you this very whimsically named duck curve. This was put together by a California independent energy operator. And what this shows is the power demanded by the California grid as a function of time on any given day. And what you'll notice is that in the middle of the day, the power demand from conventional power sources really goes down. And the reason that happens is because there's a lot of solar energy output from the solar installations in California. And what you also see here is that as the years go by, the duck is getting duckier. And the reason is that more and more power generation, renewable power generation is coming online. And what happens, the worst part of the problem is really in the evening when there is a real need for ramping up the electricity production from conventional power sources. And what can happen, and in fact, it's starting to happen, is that in the middle of the day, you get an overproduction of renewable energy. So what we really need to do is to take this overproduction of renewable energy in the middle of the day and store it, and then use it in the evenings when there is a significant power demand from conventional power generation sources. So that is the problem that we are trying to address. And the way we are doing this is by a device that looks very similar to a battery. In fact, Emily talked about electrochemistry and batteries, and I'm bringing you back to the topic. And that's the kind of device we are looking at here. But unlike the battery that Emily showed you, this is an open system in the sense that the chemicals that are needed to do this energy conversion back and forth are being supplied continuously to the system. And the way this works is that in one direction, the device functions as an electricity generation device. So it takes hydrogen, stored hydrogen, and then through a battery-like device, converts it into electricity. And that is the part of the cycle that is labeled as SOFC. SOFC stands for solid oxide fuel cell. So you're taking hydrogen and then making power from it through an electrochemical reaction. And when you run the device in reverse, when you exchange the polarity, when you change the polarity, it functions as an electrolyzer, basically taking water vapor and turning that into hydrogen. And that process happens when the device is run as an SOEC. SOEC stands for solid oxide electrolysis cells. So when you have excess power available, what you're doing is converting the renewable electricity to hydrogen, running the system as an electrolysis cell. And when you have a demand for electricity, you're doing the reverse. That is, you're taking the stored hydrogen, the hydrogen that you made when you had excess electricity available to you, and turning it back into electricity. And this is happening in a closed system. Now, the previous device that I showed you basically ran on a water vapor hydrogen cycle. But if you also include some carbon-containing fuels, which you can run as a closed system, and so there is no danger of emitting carbon dioxide, you can do this with a much higher energy density. So you're doing essentially the same thing, but now you're doing it with carbon-containing fuel. So you have two tanks, one which contains carbon dioxide, water vapor as an exhaust tank. And you take that and convert it into methane during the electrolysis cycle, and then running it as a power generation cycle in the opposite direction when you have a power demand. And I have very little time available, but I just want to show you this slide where we take a single device, and the panel on the left shows you how we operate a single device going back and forth between fuel cell and electrolysis conditions. So the tops are the fuel cell operation, one that I'm showing as 0.7 volts. And when you have negative current density, that is when the system is running as an electrolysis cell. We operated these cells up to about 1,000 hours. And now we're moving forward with a DOE-funded project, the $5 million project, where we are involving other industry partners to do this. Thank you.